Good morning, everyone. Morning. Yeah. Thank you so much for being here and bringing your energy. I love it. So as you heard, our panel is on AI in space. And many of us may have had our first exposure to that concept with HAL in 2001, A Space Odyssey. And what you will see today is that we have come so far beyond that. Our panelists do very exciting work, and our plan is that I will ask them to each spend a few minutes giving you an overview of how they use AI in space or from space to tackle difficult problems. Then I will ask them a series of discussion questions, and we will save about 10 minutes for audience Q&A at the end. So please be thinking about what questions you would like to ask them. There we go. So these are our terrific panelists, and like I said, they will each briefly introduce themselves. But we have Jasmeet Judge. Oh, actually, can you go back one first? Jasmeet Judge from Agricultural and Biological Engineering, Karim Oweiss from Electrical and Computer Engineering, Jaehan from Astronomy, and Jing from Civil and Coastal Engineering. And we will kick it off with Karim telling us about his work first. And you can either sit or stand. The remote works. Oh, the remote works now. Okay, thank you.
All right. Thank you, Rachel. It's a great pleasure to be here. I wasn't aware of this event, actually, so today, since last year. So it's a great opportunity, and thanks, David, for everything you mentioned to educate all of us about this wonderful opportunity. So my primary department is ECE, and I'm also affiliated with all these other departments. And my research primarily is at the interface between biological intelligence and artificial intelligence. So we try to address some fundamental questions about how the biological brain learns. And if you go back maybe 50 years in history, you're going to find that most of today's AI technology has been fundamentally based on findings in neuroscience. Fast forward, we still learn from neuroscience a lot. But it seems that AI technology has spun around and accelerated at a much faster pace. And because biology is incremental, it takes time, effort, and money to find new mechanisms. We thought to leverage some very, very striking advances in technology to be able to interrogate functional brain circuits at the cellular level and the population level in awake behaving subjects. It takes a lot of time and effort to do so. But what you see here, I don't know if you can see this video, but what you can see is essentially a bunch of cells in the brain of animals firing continuously. And as you can see, this morphological, nice spatial structure of these neurons tell us a lot that these are very complicated machinery. They're not just a single processing unit that takes an input and produces an output consistently without adaptation. So to apply this technology, you need expensive equipment. And this is not easy to do in animals such as rodents because they run around a lot, so we had to fix them and build a task and environment for them to learn specific things for reward. And to do so, we applied virtual reality and study adaptation as they go about learning and memory formation. We also work with human subjects who have been diagnosed with some movement disorders. In this case, it's essential tremor. And these people are medication refractory. So their only solution is to implant a lead deep in their brain called an electrical lead, essentially, for deep brain stimulation. And DBS has been FDA approved since 1996. Many people with many cognitive and movement disorders have received these implants. The thing that's new that we do here is being able to close the loop around the stimulation. What that means is the standard of care for these patients is to look at continuous stimulation. It's essentially like a brain pacemaker. But then you deplete the battery very quickly. And it causes quite a bit of side effects. So what we set to do in this case is to essentially try to, can I play this video? So essentially what you see here is one of these patients implanted with 2 leads, one that records brain activity continuously, estimates the patient intent to move, and once the patient desires to move, then it triggers the therapy immediately. And once the patient goes to rest, it dials down the stimulation therapy, and the process goes on and on. So patients are really happy with this solution. As you can tell from these spirals that are the standard task that we use, the clinicians use to assess how good the tremor control is with various stimulation programming that you can see. And what you see here in this other video that didn't play, yeah, this one. Yeah, this is the last one. So basically, we try to assess how much we're activating in the brain tissue that correlates with the tremor improvement. Turns out that AI is very fundamental for this task because you can actually detect many patterns. You have a lot of patterns of stimulation that you can apply. Some of them are good, some of them are not as good for tremor suppression. So you can generalize all of this to many, many different conditions in case this technology is needed. And that's pretty much it. Thank you.
Good morning. My name is Rachael. I'm a professor with Civil Coastal Engineering and also with Department for Mechanical and Aerospace Engineering. So my research focuses a lot on human-robot collaboration. And for this particular area of research, we deal with delays in space. And we know there are various levels of delays from Earth's orbit to lunar mission to the future Mars mission. And we found that, if the delay is shorter than 250 milliseconds, a lot of lessons we learned from robotic teleoperation can still work. And we are talking about interactive robotic teleoperation. And in this case, you can see the left-hand side, we developed a system that can engage in a more embodied teleoperation. So basically, we collect not only the vision data, but also the physical interaction data from the remote robotic system. So the human operator can not only see what the robot is seeing, but also feel what the robot is feeling. So that is working perfectly. But when we are extending the delay to about 1.5 seconds, which is pretty much what we observe a lot in Earth's orbit, unfortunately, the interactive teleoperation just start to fail. Then we focus on this method of a sensory manipulation. So to put it simple, we simulate the physical interaction before you receive the real signal. So we use a high-fidelity physical simulator to simulate, for example, the impact and also the virtual weight of an object. Although the signal, you still need to wait for 1.5 seconds to receive the signal. And even though the operator couldn't receive the simulated physical feedback and the visual feedback at the same time, we still see a great benefits of doing that using simulation. As you can see, one of the results shows that 18% of subjects reported perceived delays that are actually lower, shorter than the actual delay if we simulate the physical feedback, before the actual feedback is received. Can we go to the next slide? Yeah. Oh, that's the.
Whoops, I'm sorry.
Yeah. So if we're moving to lunar, and we know that the physical limit, the physical distance will give us about 5-second delay, but NASA just published a report and showing that the delay between Earth and the lunar can be up to 15 seconds. It's more than just the physical distance, but also the time required for processing the information, etc. So the example we are showing here is an expert from Earth doing a quick emergency ultrasound examination on a crew member. And this kind of examination requires a lot of interactive motor actions, such as the use of probe and the right angle, the right force to find the right regions on your body. So we developed this method called the sensor sharing. So very simple. We use motion captures and force capture systems. Let's say a crew member on the lunar surface and is doing everything, and we collect everything, pack everything, your experience as a data batch. And then we send the data batch to the Earth. While on the Earth, we use a bilateral control robot, a robot hand. We basically just unfold it, while the robot hand is dragging a doctor's hand and doing the same thing. So the doctor understands, oh, this is how you are doing, how you are moving, how the body of the patient feeling. And then, so the doctor can basically say, oh, let me do the next 5 seconds or next 10 seconds of action. And then the robotic system will capture all the motions and the trajectory data, pack it as another data batch, and send it back to the lunar surface. So then we are packing and sharing experience from person A, and then send it and share with person B, and we just keep doing that. So we believe that is, we're still running experiments on this, but we believe this is really good way for dealing with delays up to 15 seconds. Okay, so in the future, we're going to fly to the Mars. And unfortunately, the round communication delay can be up to 40 minutes. So in that way, there's no way for us even to pack the experience of a person and share with another person on Earth. So we have to rely on shared autonomy, which means that we have to rely on some AI to do something. So in this case, you can see we are developing this foundation model, transformer-based foundation model, to understand the operation sequence of a very complex piece of equipment. And we can send this understanding of a sequence order to augmented reality headset, so the operator, the astronauts, can see the operation steps as animations. So basically the operator doesn't need to understand what's going on. The AI is trying to understand that. But we still believe human should still be on the loop, at least. So supervising what's going on. And unfortunately, this is still the most challenging part of our solution because we still don't trust AI. So that's why our latest work focuses on trying to understand, how AI is making decisions. And we believe that AI is making decisions in a way very similar to human decision makers, which we can talk more later. Yeah, thank you.
Thank you.
Okay, thank you. Hello, everyone. My name is Jaehan. I'm from Astronomy department, and I'm also a member of AI Square Center and also newly launched Space Institute at UF. How do I proceed? Okay. Yeah, so as an astronomer, I study planets, not only the planets in our solar system, but also exoplanets, extrasolar planets. So what you are seeing here is a diagram showing the discovery of a lot of exoplanets, as you can see from all those circles. And those orange squares are the solar system planets. So on the y-axis, you see the planet masses relative to Jupiter. So if you see one, it's Jupiter mass. On the x-axis, that's the distance from their host star. So in our case, that's the sun, but exoplanets have their own host star. One is 1 astronomical unit. That is the distance between the sun and the Earth. And both x-axis and y-axis are in log scale. So you can see kind of the demographics of all exoplanets. And at this point, astronomers found as a community about 6,000 exoplanets. And the number is, as you saw, exponentially growing. So what do? I'd like to search for the youngest exoplanets. If you Google youngest exoplanet in our galaxy, you will see my name popping up. So do it later on, a New York Times article on it. But anyways, so why do I study youngest exoplanets? The reason is that I want to learn how planets form, how planets in our solar system, including Earth, formed in the past 4.5 billion years ago, and how life emerged on Earth and maybe other planets or moons in our solar system, and some of these exoplanets, right? And I usually, use this example of for example, you have cell phone, you have car, you know what makes them, you know what building blocks are, but you don't have all these instructions. And also, if you think about a Lego, very complex one, I have one. Maybe Star Wars, you have one. The most complex one we have at our home is my 5th grader's Statue of Liberty. This is like this tall. It has instruction book like this thick. It's like 200 pages, and it comes with like 1,000 building blocks. So we know we use 1 by 1, 2 by 2, 8 by 2, all those blocks, and we know what to make, but we don't know all the intermediate steps of 200 pages. And I'd like to make those books by looking at youngest planets that are forming right now elsewhere in our galaxy. So that's why I'm interested in searching for and studying youngest exoplanets. So how do I do this? As an astronomer, I need to show these beautiful pictures. So this is an array of antennas down in Chile, Atacama Desert. There are about 50 telescopes looking at the night sky, and we collect data and then combine later on, and then we make great images. That's how we, discover. That's one of the ways we discover exoplanets. Okay, so this is kind of the data that we see. This is three-dimensional data cube. So on the x-axis, y-axis, this is just a direction, x-axis, y-axis on the sky, RA or declination, if you're familiar with those terms. The z-axis is a little complicated. It's velocity, line of sight velocity. Don't worry about it. But if you think about medical imaging, this is exactly the same. So if you go to hospital, I hope this doesn't happen to you, but if you ever take CT scan or MRI, you have three dimensions, x-axis, y-axis, and z dimension, right? That's exactly the same thing. And then in medical imaging, medical doctors see CT scan, MRI, try to find some anomalies like tumor in brain. That's exactly what we are doing here. Using convolutional neural network, we try to find signatures that are created by forming planets right now in that particular system. So that's how I use AI and machine learning. This is an example. So this is the left is just one slice of the observational data, and within the circle there's some little Thunderbird-like pattern that shows up. That's what we believe is created by forming planets in that system. And those two on the right is my training data set where I don't have any planet. You expect to see very smooth data because there's no planet at all. On the right-hand side, there's a simulation where I put a planet, and then you see pretty similar feature, the Thunderbird feature pattern that develops. So again, using convolutional neural network, I'm trying to find these features in actual observational data. And from there, we start to thinking about how fast these planets form, how big and where, and how those planets form. And then hopefully we think about life elsewhere in our universe. So that's what I'm doing. Thank you.
Thank you. Good morning, everyone. It's great to be here. I'm looking forward to the panel and also the rest of the talks today. So that's a very exciting day. So I'm Jasmeet Judge. I'm at Ag and Bioengineering Department. I also have two hats today. I'm also the director for Center for Remote Sensing. And for just quickly, I would like to briefly introduce the center and just mention this center started like in early 2000s, late 1990s, with a vision to be the remote sensing center. So I work in remote sensing, particularly satellite remote sensing. So it's AI from space, not in space. So we're looking down. So to be the premier remote sensing center, advance science and technology, and form interdisciplinary teams. We currently have about 75 affiliate faculty from across 26 departments and 4 colleges. And we have enabled lots of collaborations, very unusual kind of collaboration, agronomists working with astronomers and entomologists working with people in electrical and computer engineering. So there partnerships that normally we don't see. So I encourage you to go to our website and look at it. And we have people who work in satellites, UAVs, all kinds of stuff as well. So for my research, I work with satellite data. So this is a slide showing the kinds of satellites that NASA has. So these are satellites that are providing global information free of cost every so often, depending on your temporal resolutions. And this is NASA. So now you have ESA has also these satellites. So now we are in an age where there's tons of data. So we had, like in early 2000s, we had a data-driven explosion of data-driven machine learning and data-driven methods because of these kind of data sets. And so the typical use of satellite data in agriculture, if you're not familiar with it, is crop type and structure, crop nutrient status, people are working on it, and health, crop function with phenology, crop growth, and then water in quantity, how much water is there in different kind of hydrological cycle components, and quality, and then also water state, whether it's frozen and thawed. And in some Midwestern places, it's important to know when it thaws because that's their planting time. So these things are really important, and satellite is really helping us do that. So just 2 examples I'm going to show, given the interest of time. AI, we've been using many moons ago. We've been doing this almost for a decade, spatiotemporal scaling. And at that time, we didn't call it AI, right? AI is something we used to think of robots when we thought of AI. But now it's like AI is for everyone, like we said. So we did clustering-based, regression-based methods to take a coarse scale image of, let's say, soil moisture here, and do AI-based methods to get downscaled or true soil moisture from there. And then we moved forward to do spatiotemporal scaling, where you have multiple data sets that are coming in different space and time resolutions, and you combine them and do coarse and true kind of you compare it, and you start getting structure from the coarse, merging with other data sets like land surface temperature, precipitation, LAI, and those kind of things. So we could do that. And then now we are moving towards in-season crop growth estimations and even predictions using model and data integrations. For example, typically people have used data assimilation or optimization techniques to incorporate remote sensing data into the physically based models to improve the models. And then there were data-driven methods that we talked about. But data-driven methods take tons of data, and then with remote sensing in the past, we didn't have that much data. Now we have tons of data. So if we can actually integrate the data that is coming from satellites and also the 20, 30 years of our experience with model development and understanding of the physics, that is like the holy grail kind of a thing. So for example, you have corn and growth. This is just an example. All these export countries there, but only the yellow countries, Argentina and US, provide crop progress that's publicly available. So you see, in most of the world, you don't have crop information, even though they are exporters, for any kind of yield estimation or any kind of insurance or any kind of risk estimation. So what we have done is we have combined different crop models and remote sensing models and weather generators. So we work with multiple people. This is a very collaborative effort across computer science departments and crop modelers and stuff. And then we build a machine learning method to do that. And when my student was doing this, I expected what? You're used to accuracies of 98% in papers, right? And with AI-driven methods, I don't know how they get that. But so we thought, I truly thought we know nothing about Argentina at this point because we have no data there, infrastructure, poor infrastructure. So what will we get, 20%, 30%? It's hidden there. My punchline is hidden. Can you believe it? I'll say it anyway. So it's up to greater than 70% accuracy. So that was just a mind-boggling thing for me to be able to combine these things to do that. So, yeah.
Perfect
Yes,
timing.
I timed it. Yeah, so I just wanted to let you know, this is just a flavor of this. There are lots of new ways to merge models and data sets, especially satellite data sets, and new satellites are coming up. So we're continually developing new methods. Thank you.
So thank you, panelists, for sharing your incredibly exciting and super cool research. I'm going to ask you a couple of questions that are a little more forward-thinking, and I invite you to please share your thoughts with the audience. So this first question is directed at Jasmeet and Jaehan. So I'm curious about how you and your field will use AI in the future to better understand our planet and other planets. So what do you envision in the future that's coming?
So that's an excellent question because with more and more data coming in, we are having interesting issues in spatiotemporal scaling issues. New issues are coming up there. And then the biggest unknown right now is improving our prediction capabilities. And I think that's where AI can really, really help, is not only learning from the current research and models and all that stuff we have, and some of the models don't work in extreme conditions of drought and floods, and predicting those in a timely manner and do disaster mitigation is going to be really huge for in our field. I think the prediction part of it, using AI would be the biggest thing.
Yeah, so speaking about other planets, exoplanets, I think it's also data-driven at this point. We are getting a lot of data. In the future, in few years, I showed you ALMA, that's the telescope array with 50, like 12 meter each diameter. But we are building something called a square kilometer array. So it's filled with hundreds of antenna. There's another array in Australia which has each of those are like 2 meters tall, but there are like more than 100,000 telescopes. And the number of the size of data we are taking will be it's tremendous. It's let me do this correctly. It's like over 10 terabytes per second that you are getting, and over 7 zettabyte per year. I don't know what zettabyte is. It's like billion terabyte. I never dealt with that large data. So that's the amount of data we'll be getting in just few years. And AI, machine learning, it's, I would say, inevitable at this point. So what we are going to do, astronomers are going to do with those telescopes in the future, is to try to find some complex organic molecules, something like amino acids. Those are base of DNA, RNA. So can we detect those molecules, amino acids, complex molecules in some area in other exoplanets? Can you tell something about life, maybe emergence of life in the future or right now at this point? Yeah, those are some key questions that we are trying to answer as a community, as astronomers, and there's again a lot of data that will be coming. So super excited, but AI is key component there.
Great. Thank you. So my next question is for Eric and Karim. Can you both please comment on how you and your field may be using AI in the future to better understand human performance and central nervous system function in space? So thinking about humans or other animals in space.
So first of all, we have to admit that humans are very complex. And so it's kind of like telling where the fish are by telling the change of the water waves, right? So I guess to deal with this kind of complexity, we have to use another complex system to understand that. So for example, we are using a lot of sensors, FNIRs, eye trackers, and we are collecting motion trackers, we are collecting multimodality data. But the end is we still have huge variations in our data, so it's so difficult to understand Python. While a lot of AI tools are a great Python machine. They understand Python, right? And understand Python in a way that we don't understand yet. So I guess in the future, we're going to see more and more use of advanced AI models, large models, to understand human data and to the scale. Yeah.
Right. So in terms of AI in space for human health, I think it's important to realize that preserving brain health is the most important for the crew, for astronauts. These people spend many, many days, months, years in space where microgravity and radiation levels are not something that the human brain has been used to. So being able to understand what's happening to the brain during these journeys is super important. The second point is developing countermeasures, basically equipping these astronauts with tools that can help them, not just regular physical exercise, in spaceships, but really, ways that they could alleviate all the adverse effects that we know of when they come back to Earth. And the study of neuroscience and neurobiology helps us a lot in trying to understand how we can mimic this in animal models. On Earth, we don't have to send animals in space, or we possibly can do that if the opportunity arises. But it's important to be able to understand this and develop the right tools for the human health.
Okay, great. Thank you. So my next question is for all of the panelists, but I hope that this question and their responses also kind of get the audience thinking a little bit about how you might be able to get involved using AI in space or from space. So I'm going to ask our panelists, how can others collaborate with you, and what kind of collaborative needs do you have for your work? And I think when we start talking about space, people get very excited and very interested and want to collaborate with you. So what is the path, or what needs do you have?
Well, the easiest thing is to drop me an email. No, I'd like to definitely educate myself a lot more about what other thinks of AI, not just in space, but their use in their daily lives, right? Beyond education. People get excited about ChatGPT and whatnot, but we have to recognize that ChatGPT's success story is based on two important things. One is the availability of a humongous amount of training data, and second, the wonderful NVIDIA chips, right? Are we there yet in terms of the ability of these AI tools to reason? I don't think so. We might be there in 5-10 years, who knows? But I think it is important that we recognize the dimensions of the problems that we're trying to solve with AI, and recognize the limitations of the AI tools so that we don't overpromise and underdeliver.
Can you pass this?
Sure.
Thank you. Thank you. So in terms of collaborations, I think that those are key, because I'm not a foundational AI person, and AI changes every 2 weeks, right? So by the time there's a Python toolbox for me to use, it's already not cutting edge, right? It's already a state-of-the-art thing that you can use for applications. So I think we would really need to partner with people who are pushing the technology of AI themselves while they understand it, but then kind of work together so they understand our language too. I think that bridge is very critical, and it's not very organically formed. So we need to really spend a lot of time in strategizing and partnerships and cultivating those, so we can build bridges and form teams to work together. I think that's the key to getting success in both applications and also foundational AIs.
Yeah, I can also echo what Jasmeet just said. I'm an astronomer, but I was never, officially or professionally trained as a computer scientist, right? So in the end, I'm an astronomer. And I don't know if this is the thing panelists should say in this kind of setup, but I didn't know anything about AI until like 5 years ago. I learned by myself. I took I watched YouTube videos. I took some online courses just because I wanted to use it. I thought there will be a great opportunity to use these machines in astronomy. So what that means is that, again, I'm using convolutional network and other stuff, but it's probably outdated, right? So any collaboration with computer scientists who are an experts in machine learning AI, that would be great. And UF is great because David just said at the beginning, we have a lot of experts, and we actually teamed up between astronomy department, a few faculty in computer science. We proposed to build an institute, and also some colleagues from Vanderbilt and Georgia Tech to build AI in space, this exact thing in the southeast of US. So that's starting to build up. But also I'd like to highlight that astronomy as a field is so interdisciplinary at this point. So it's not just astronomy or physics or computer science. If you think about life, we need to understand what biology is doing, what chemistry is doing, what geology is doing. So even if you're not computer scientists, there's a lot of opportunity to collaborate to find exoplanets and life.
So I think the best way for us to work together is let me buy you a cup of coffee and let's have a chat. Sometimes I feel in the past 2 years I feel like I'm a large language model. What we discovered is the recent models have this great in-context learning ability. It just show the model some examples, a few examples, and the model happens to have the ability to learn that. So I feel like we also are this kind of in-context learners. Once we are exposed to information from other disciplines, our brain can adapt to that information very quickly and start to develop this kind of logic that can fit into that new context. But chats, conversations, that is prompt engineering on human beings. So once I'm exposed to your research, and once I'm exposing my research to you, I gotta open up some kind of a process, transformer process in our brain that definitely will engage in this in-context learning. So be transparent, willing to share your research and willing to share my research, and that will have open up more and more research opportunity and maybe new research directions.
Great. Thank you, panelists. So my next question, I think Karim and Eric already talked a little bit about the future of AI in space for understanding human performance, central nervous system structure and function. But I'm going to ask you guys to go a little bit farther, because I think people are very excited about NASA's plans to send people back to the moon and future plans to send people to Mars. So can you guys comment in how you see AI being able to play a role in those future missions?
So I think autonomy is key, and human-machine interaction is another key. The ability for humans out in space to be able to interact continuously with machines so that they don't compete with one another, they complement one another. And figuring out what can be relegated to the machine to make autonomous decisions in uncertain environments, or ones that have to be relegated to the human. I think that's a fundamental question that we sort of trying to get an answer for, but we're not there yet.
I think the critical step is AI alignment now. So we need to align the goals of AI and human agents, and not only just from the ethical perspective, but also the high order decision-making process. So when we're reaching a decision outcome, actually it's a very complex process. We process very limited information. We generate a belief about the state, and then we select what is important and what is not. And finally, we also calibrate our thought, which is a metacognitive calibration. So unfortunately, we don't quite yet understand how AI is engaged in such a complex decision-making process. So in order to use AI, to be able to use AI, by the way, NASA doesn't like using AI, for this kind of autonomy yet. In order to be able to be confident to use them in the future, especially on Mars, we need to understand AI using a more like human-driven cognitive process, a cognitive framework, so we have the confidence. So I think that's probably a very critical step now.
Okay, so now, audience, is the time where we invite you to participate and ask our panelists questions. There's a microphone here in the middle of the room. So if you have a question, please raise your hand. And I hope, I saw a lot of you drinking coffee, nodding your head, so hopefully there's a lot of good ideas and questions.
And I'll bring the mic to you. So just
There's one right in front of you, I see.
Oh, I don't think I need the microphone. Thank you, Doctor. Yes, so I have a technical question. What is it? So Git, in my experience, is very poorly suited to producing like reproducibility in AI. It doesn't do large file sharing very well. It doesn't like doing like small changes. You can, but it's not suited for it. So I was wondering what platform or platforms you all use for sharing these massive data sets, and like what sort of environment you use. You don't have to get like crazy technical, but I just know that like right now the computer science like gold standard for reproducibility is like the opposite of what you would do with AI research. So I was just wondering what you guys use.
Do you want to comment?
HyperGator. So that's no kidding. We're actually using HyperGator on a daily basis. We fine-tune models. The speed is amazing.
Yes.
I'd add to that, it is important to recognize that if the public domain, you're gonna get users who may not be very familiar with the details of the data you're sharing or the code. So it is important before releasing these things in the public domain is to ensure it's curated well enough, documented, so that anybody can use it. The more you spend time on these things, the more widely disseminated they're going to be.
Yeah, I can also comment. Yeah, so NASA and NSF, they also pay attention to open data. And we, when you write grant proposals, we all need to write data management, right? So what we often do as an astronomers is that, for codes, it's light enough so that we can just put it in GitHub. NASA also owns its own platform so that we can share things. But when it comes to data, as you said, it can be very big. What I personally use is Zenodo, but it has maximum of 50 gigabytes. So that's probably not enough for many data sets that we are using, like astronomical data that I talked about. But unless we can provide some final products so that people can at least reproduce from there. Yeah, and again, Hypergator, it provides a lot of disk space. So that's good. So hopefully this answers part of your question.
Oweiss, right?
Yes, Karim.
I wanted to ask about a little bit more information about how you were talking of figuring out how being out in space, being out exposed to radiation and different gravities, how that'll affect anything neurological, right? So I just wanted to kind of ask for kind of an expansion on that because I think it's really interesting. Are you really just trying to focus on using AI to predict what will happen, or are you grabbing data from people who are in the International Space Station, or how is it happening?
It's all of the above.
Oh yeah.
So an important feature of the human brain is the extent of its excitability of its cells, right? And by that I mean the ability to recruit brain cells, regions, pathways to perform certain function. And the brain has a very simple principle: use it or lose it, right? So if you think of astronauts who are just laying in bed for many days, many months and so on in space ships, that's very detrimental to the health of the brain. So when we try to think about that, we try to mimic things on Earth with animal models. Of course, it has its drawbacks. We can't answer every single question. But the fundamental question is, to what extent changes are happening in gray matter, in white matter, as a function of the experimental control variables that we subject the organism to. Of course, we always follow ethical work with animals and so on. And there is a lot of published literature regarding how you can mimic those in animals. Like, for example, there's a model called the hind limb unloading model for rodents, where you just lift the animal's, hind limbs to try to mimic, the posture where an astronaut would be laying in bed for extended periods of time. And then you look at what happens to the brain, right? Has the brain activity shifted in measurable ways? Has the performance of the animal changed in a particular task? And these could be simple motor tasks, or they could be other more complicated tasks, such as cognitive tasks, navigation in virtual environments, things that we try to kind of enrich the environment so that we can study all aspects in all dimensions of the problem. But we're just starting this, so I can't really give you concrete answers about what we found. But based on my reading and my group's reading of the literature, there's quite a bit of things that develop very rapidly in the brain on the span of hours. So we're hoping that our limited experimental time, where we observe the animals, can tell us something about what's happening.
And thank you. If I could ask one more follow-up question.
Sure.
I know you just mentioned that you don't really have a lot of information yet, you just started, but what do you hope to achieve with this? Is it you're trying to maybe make prevention of any serious detriment to the brain, or are you really trying to make recovery efforts better?
Right. I mean, one of the things that one would fear is, the cells die, right, because of whatever. So if there are ways that we can rescue and preserve the health of the cells, their excitability, their function, whatever, hopefully that would, educate, human research on what astronauts need to do in case they have no other choices but this solution.
Thank you so much.
And maybe I'll just take moderator's prerogative and add to Karim's answer, because this is also the area in which I work. So Karim's work in non-human animal models, I think, can achieve a lot better mechanistic understanding than what I do, which is I'm working with human subjects. And so you asked, how do people study this? So with NASA funding, we typically collect a huge amount of data from crew members before they go to space, behavioral measures, brain scans of various kinds. But the spatial resolution we have is not as good as what he can get. And then while people are on station, they also do experiments for us, so tests of cognitive function, sensory motor function, and then we scan them again when they come back and follow them out to a period of several months. So we have learned a lot already, but there's still so many answered questions about mechanisms of changes. How can you predict who will change more than others? How can you develop countermeasures? But I will circle this back to some of the other questions. A lot of the data that I have collected are widely, they're available and accessible. They're in NASA's Life Sciences Data Archives if anybody wants to download them and work with them. But the beginning of the space station era, crew members were going to the space station and building and assembling it. And now they are going to conduct science and participate in science. And so there's a lot of fantastic research taking place. I think we have time for maybe one more question, if we have one. There's one back there.
Good morning. My name is Rachael, and thank you so much, Dr. Reed, for your leadership for our AI Square, and Rachael is fantastic panel discussion. My question is back to your original question about forward thinking. I would like to ask our panelists, how would you foresee in the future and how fast that we are going to have astronauts lead space shuttle, and we are going to use robotic arms to do all the experiment in the space, and the people with expertise could control the robots from the space.
So I think the question is about people controlling robots from space, and there is already a little bit of that, right? It's manual control, for instance, of the robotic arm, the Canada arm. But maybe the question is a little more about like additional robots, or can you elaborate?
Yes, and how the robotics development and the revolutions could forward all the science to the next level.
So Eric, maybe like advancements of robotics?
So like this Rachel mentioned, I think NASA has been doing this already. Some astronauts controlling robot in space for operations. I guess maybe the next step is to have more like a mixed control strategies. Like we can set astronauts free from all the manual control tasks, and we can focus more on the high order commands from the astronauts, while the robots can finish some fundamental tasks, right? And maybe even in the long future, we are talking about more like a supervisory control. So the astronauts will focus on giving the highest order of highest order of instruction, while the robot can finish the task on their own. I guess that's my answer.
Thank you.
Okay. So I think we need to wrap up. So please help me in thanking our panelists for sharing their exciting work and their ideas.